Namaskar, my dear friends. So we have seen almost everything about linear algebra matrices. So like what is matrix, what is the determinant, their properties, and lot of various features and functionalities. Okay. We have also talked about how to find the determinant of a square matrix and various properties like when it will be singular, non-singular, how to find the inverse of a matrix, how to find out, solve linear equations. Then we have also identified, how to get rank of a matrix, or we want to find the eigenvalues, eigenvector, then Cauley-Hamilton theorem. There are various things that we have seen about matrices. This is going to be the last topic of matrix algebra. So in this particular thing, what we are going to talk about is special matrices. So there are a lot of places, or there are a lot of situations where special matrices are coming. Okay. So in this case, we'll talk about various features of a special matrix, how we can solve questions based on that. And there are a lot of the questions that has come in GATE based on these properties, or this particular special matrix. So let us start. So number one is symmetric matrix. Symmetric matrix. Symmetric matrix is called as A transpose is equal to A. So what happens is, if there is a matrix A and if you find out its transpose of the matrix, so you know already how to find the transpose. You have to just replace the rows to columns and columns to rows. Like you have to interchange the columns elements to rows element and rows elements to columns element. And in that case, if both of them are same, then it will be symmetric matrix. Okay. Number two, skew symmetric matrix. Skew symmetric matrix. In that case, what happens is, if you find the transpose of a matrix and if it is going to be equal to negative of the matrix A, okay, then it will be skew symmetric matrix. Okay. The third one is orthogonal matrix. We will take examples and questions and all. So if a matrix is said to be orthogonal, it means it must satisfy this particular properties. What happens is, if you multiply the matrix to its transpose matrix, or you multiply the transpose of a matrix to its matrix, this must give you the identity element. Okay. So if you are getting identity element in any of these cases, A into A transpose or A transpose into A, then that matrix A will be called as orthogonal matrix. Okay. Now let us talk about other parts. Next one is conjugate of matrix. So conjugate of matrix, how to find out conjugate of matrix? Because there are lot of occasions where we need to identify, or we need to find out the conjugate of given matrix. Okay. So it is represented by A conjugate. Okay. And this can be found out by replacing all the elements by its conjugate elements. Okay. So there are occasions where all the elements are, or some of the elements are complex elements, complex numbers. So to find out conjugate of matrix, you have to replace them by conjugate of the elements. Okay. So replace the elements of matrix A by corresponding conjugate. Okay. So let us say, for example, I'll give you an example so that you can have a better understanding about it. Let us say we have a matrix A which is going to be 1, minus I, minus 2 plus I, and let's say minus 4. So what will be the conjugate of a matrix A? So A conjugate, that will be equal to, replace them. Before that, can I give you an example? Let us say Z is an element which is A plus IB. So what will be the Z bar or Z conjugate? That will be A minus IB. Understood? Or for example, let us say Z is equal to 3 plus 2I. So Z bar will be, or Z conjugate will be what? 3 minus 2I. So your aim is to understand that how to find the conjugate of a complex number. So very simple. So if this is real number 1, so that will remain as it is 1. Minus I will become plus I, and minus 2 plus I will become minus 2 minus I, and this will be as it is 4. So this is the conjugate of the matrix. Okay. This is also called as image of Z on x-axis. If you want to find out this particular element, this is called as image of Z on x-axis. How to visualize this? Let us say this is my axis. So what will be where is the value 3 plus 2i? So can you tell me, let us say 3 is x-axis and 2 is y-axis, right? So let us say this is the value 3 comma 2. Okay, so this is my real and imaginary and real. So now if you find out conjugate of this element 3 minus 2i, where is 3 minus 2i? Down. Okay, so this will be, let's say, somewhere here, 3 minus 2. So as you can see very nicely that this is my 3 plus 2i vector, and this is my 3 minus 2i vector. Okay, so you can see it is an image on x-axis. This is my x-axis, this is my y-axis. So you can see the image of point, let's say P, is going to be Q, which is nothing but conjugate of Z. Understood? Now let me tell you one more, properties of this particular thing. So let us say if my Z bar is equal to Z, or conjugate of Z is equal to Z, then what will happen? It means basically you can say that 3 is going to be equal to 3. It is the only case when my Z is real. Okay, so I can say real number. You can see all the elements of, all the elements of matrix A which are real remain same in conjugate also. Okay, so if Z conjugate is equal to Z, it means Z is a real number. What will be next? If my Z bar is equal to minus Z, so let us say this was minus iota, it become plus iota, right? Plus I. This will happen only when only the imaginary part is remaining. Okay, so you can see, so you can say that this is purely imaginary, or you can say 0 also. If the element is 0, either you can say minus Z or not, doesn't matter. Okay, so this was all about conjugate of a matrix. Now let us talk about the next one. So what is going to happen is conjugate transpose. So in this conjugate transpose, we have already seen transpose of a matrix, but now we want to find out conjugate, and then we want to find out transpose. So this is called as little differently, which will be a to the power theta. So a theta is nothing but your conjugate transpose, and this can be represented by, you find out the conjugate of a matrix element A, and then you find out the transpose. So what is the first step? Replace all the elements of matrix A with their conjugate, and then find the transpose. That can be represented by A theta. Okay, this can also be done by find out the transpose of the matrix and then find the conjugate. Okay. So let us say for the above example, A was what? We had A was like -1 I -2 -3 plus I. Let us say some other example we are going to take. Now we want to find out what is my A theta. So to get A theta, first of all you have to find out A conjugate, and then we have to find out A conjugate transpose. Understood? So this is the rule that we have to follow. So let us do that quickly. Can you do that? A transpose, A conjugate is what? Replace all the elements of this matrix A by their conjugate. So that will become -1 minus I -2 -3 minus I. Now to get A theta we have to do what? To get A theta we have to do A conjugate ka transpose. So to get this, you have to keep all the elements, rows elements to column. So can we do that? -1 minus I -2 -3 minus I. So this is your conjugate transpose of the matrix A which we have written here. Understood? Good. Let us take the next property. The next property is based on this conjugate. So you can remove that number and write down fourth again. Hermitian matrix. Hermitian matrix. In that we had seen symmetric matrix, skew symmetric matrix. Similar to that we have Hermitian matrix, skew Hermitian matrix and all. So that will be for complex conjugate, like complex matrices. So Hermitian matrix says that if my A theta is equal to A, then it will be Hermitian matrix. Okay. And this is nothing but a general form or generalized form of symmetric matrix. So you can write down this is generalized form of symmetric matrix. Understood? So this was Hermitian matrix. What about next? Skew Hermitian matrix. Okay. So let us say fifth one, skew Hermitian matrix. So in that case what will happen is my A to the power theta is going to be equal to minus A. So this is also called as generalized form of skew symmetric matrix. Understood? So skew Hermitian matrix is nothing but for the conjugate transpose of matrix is going to be equal to negative of the matrix. Okay. Next properties in special matrices is you can write down unitary matrix. Unitary matrix. In unity matrix, you can see that we have A into A theta must be equal to A theta into A is going to be equal to I. Understood? So similar to the orthogonal matrix, we have unitary matrix, and unity matrix is a generalized form of orthogonal matrix you can consider, where A into A theta is equal to A theta into A, that is going to be equal to identity matrix. Okay. So quickly we will write down 2-3 properties based on this particular conjugate ones and other ones. So one more is idempotent matrix. Idempotent matrix. So a matrix is said to be idempotent if its a square is equal to same value. Okay, so A square is equal to A. Let us say a matrix A is given, and if you find out A square, like you multiply A into A, if it is possible, then it will be called as idempotent matrix. Next one is involutory matrix. Involutory matrix says that if you find the square of a matrix and if it becomes identity matrix, okay? So like a matrix A is there, and if you find the square of that matrix and it comes identity matrix I, then it becomes involutory matrix, okay? Next one is nilpotent matrix. So nilpotent, it says that if I find out a to the power k, where k is any number, that makes is a zero matrix, okay? If that makes it a zero matrix, then it becomes nilpotent matrix. So what is the understanding about k here is, you can see that k is least positive integer. Least positive integer, okay? And k is actually called as nilpotent matrix index, okay? K is called as index of nilpotent matrix A. So the least value of k, which will make the value of a to the power k to be a zero matrix, then it is called as nilpotent matrix. All right. So this was all about different kinds of special matrices. Now what we'll do is we'll see the properties of each of them, or maybe most of them, okay? So that it will be very useful for you to crack any kind of questions that is coming in your GATE examination. All right. So let us see that properties. So if you talk about properties, let us say number 1. We have every real square matrix can be expressed as the sum of symmetric matrix and skew symmetric matrix. What I mean to tell you is, let us say a matrix A is given that can be expressed as P plus Q. Okay, it means what? A matrix A can be represented as the sum of a symmetric matrix plus an skew symmetric matrix. Okay, so where P is symmetric, Q is skew symmetric. What I mean to say, you can write it down. Every real square matrix can be expressed as a sum of symmetric and skew symmetric matrix. Understood? It means A will be equal to P plus Q. Now you will ask how to get the symmetric form, I mean skew symmetric form and symmetric form. So the symmetric form can be found out by, let us say P is my symmetric matrix, that can be found out by A plus A transpose by 2. So you already know how to find the transpose of a matrix. So if you do this, you will get a symmetric matrix. So if you want to find out your symmetric portion, then you have to do this operation. If you want to find out a skew symmetric portion, then what will happen? My Q will be equal to A minus A transpose by 2. So this is my skew symmetric. Understood? So this was all about expressing your matrix in the form of the sum of symmetric matrix plus skew symmetric matrix. Let us take the next property. So the next property is the determinant of orthogonal matrix is plus minus 1. Okay, plus or minus 1. The determinant of orthogonal matrix is plus or minus 1. How to find that? So you already know for orthogonal matrix, my A into A transpose is equal to I, right? Like if you multiply the matrix and its transpose, that must be equal to identity matrix. This is nothing but your orthogonal matrix property. So can we quickly do that? If A into A transpose is I, then can I write it down? The determinant of A into A transpose must be equal to determinant of I, which is nothing but your 1, right? So you already know that the determinant of two matrices A, B can be equal to determinant of separate matrices A into A transpose can be written as I. Understood? And you already know the determinant of A and A transpose both are actually same. So can I write it down? Determinant of A into determinant of A is equal to 1. Got it? So it can be also written as determinant of A square. Understood? So you can see determinant of A 2 times is going to be equal to 1. It means I can write it down, determinant of A is going to be square root of 1, that is plus minus 1. So this is how you can say that determinant of orthogonal matrix is plus or minus 1. Okay. Now let us talk about the other part. So next property is, if A is orthogonal matrix, if A is orthogonal matrix, okay, then we can say my A inverse is nothing but A transpose. So finding A inverse of a matrix is very difficult. You know already, their long process, right? So if you already know that matrix which was given is orthogonal, then you can just find out the transpose of that matrix to get the inverse of the matrix. Okay. So why it is so? Like can we do that? Can we prove that? So yes, we can prove it. Let us say you know already that for orthogonal matrix we have A into A transpose is equal to A transpose into A, which is going to be I. And you already know that we have what? A into B is equal to B into A is equal to I. Then B is nothing but your A inverse. Yes or no? So if B is equal to A inverse, it means A transpose here will also be A inverse, because A into A transpose equal to A transpose into A. So this A transpose is not acting as a element B, which is going to give you I. So can I write it down? Can I write it down? Based on this property, A into A transpose is nothing but A into A inverse is equal to A inverse into A is equal to I. And by comparing this equation and this equation, we are going to get A inverse is equal to A transpose. So you understood? If my matrix A is orthogonal matrix, its inverse will be A transpose. Let us take the next property. It says that principal diagonal element of skew symmetric matrix are always 0. So the principal diagonal elements of skew symmetric matrix are always 0. Like there is no way to find out having elements non-zero in principal diagonal, it is to be skew symmetric. Okay, like you have already known that A transpose must be equal to minus A. So the principal diagonal elements of this matrix A must be 0. Okay. Next property is similar to that, diagonal elements of Hermitian matrix are real number. Okay. So what happens is, let us say, what is Hermitian matrix? A theta must be equal to A, or it was also like A conjugate to the power transpose is going to be A. So this was Hermitian matrix. So if it has to be Hermitian matrix, the diagonal element of Hermitian matrix is real. The diagonal elements of Hermitian matrix are real number. Understood? Let us take the next property. We have diagonal element of skew Hermitian matrix are purely imaginary or 0. So here in real ones we had always 0, but for skew Hermitian these principal diagonal elements can be 0 or purely imaginary. So you already know what is skew Hermitian. A theta must be equal to minus A. Got it? So in that case the diagonal element of skew Hermitian matrix skew Hermitian matrix are purely imaginary. Imaginary or 0. Got it? Next property is the eigenvalue of symmetric matrix are always real. So let us say you have a matrix A which is symmetric. You already know the properties of symmetric matrix. Its transpose will be equal to the matrix. So the eigenvalue values of symmetric matrix or otherwise you can take it up as Hermitian matrix also are always real. Why I am telling you this property is you will understand later on that they are very useful, because GATE is asking question based on the properties, like if all the eigenvalues of a like matrix is real, then what is the possibility? So the possibility is the matrix will be symmetric or Hermitian, is like Hermitian matrix, something like that. Okay. So based on this property, can we find out another property? Like for symmetric matrix, if it is real, then for skew symmetric, what will be there? The skew symmetric, it will be imaginary or 0. So we can write it down. The values of skew symmetric or skew Hermitian. Okay. Matrix are purely imaginary or zero. Or 0. Okay. Let us take the ninth one. So property number 9 is the eigenvalues of what is remaining. We have seen skew symmetric, symmetric, and then we are remaining with orthogonal matrix. So the eigenvalues of orthogonal matrix, or that is also unitary matrix for complex numbers, right? Or this is also called as unitary. are are absolute value 1. Okay. It means what? I'll tell you. I'll give you the examples. The eigenvalues of orthogonal matrix or unitary matrix are absolute value 1. It means, let us say, the absolute value of lambda is my eigenvalue, that must be equal to 1. So for example, let us say if one of the eigenvalue is 1, another will be -1. If let us say I, it will be -I. If let us say 1 by root 2 plus I root 3 by 2. Understood? Why? Because the magnitude of this one will be always 1. You find out a square plus b square k square root, it will become 1. And if it is complex like this, the other value can be easily written as 1 by root 2 minus I root 3 by 2. So the complex eigenvalues always occurs into conjugate pairs. Alright. Let us take the next property. If lambda is an eigenvalue of orthogonal matrix, eigenvalue of orthogonal matrix, understood? Then 1 by lambda is also an eigenvalue. So if an orthogonal matrix is there and it's one of the eigenvalue is lambda, then 1 by lambda will definitely be another eigenvalue. Okay. So it is very easy to get the other eigenvalue if you know the value of eigenvalue is lambda and that matrix is orthogonal matrix. Okay. Now let us take the another pairs. So let us talk about the eigenvectors corresponding to distinct eigenvalues of symmetric matrix are pairwise orthogonal. Okay. So what I am going to tell you is this is very important statement because several times GATE has asked questions based on this. Okay. So the eigenvector, what I mean to tell you is the eigenvectors corresponding to distinct eigenvalues. Let's say we have two eigenvalues then of a symmetric matrix. Then what will happen? Their eigenvectors will be pairwise orthogonal. What it means? Let us say two vectors. Let us say two vectors. One is x, which is going to be a, b, c, and one other one is, let's say, y, the eigenvector, which is going to be d, e, f. Okay. Then what will happen? They will be orthogonal when x transpose into y will be 0. It means a, B, C multiplied with D, E, F is going to give us 0. It means what? If you multiply them, what will happen? AD plus BE plus CF is going to be equal to 0. So then it will be called as orthogonal. And if the matrix was symmetric matrix, then the eigenvectors will be definitely orthogonal to each other. Okay. So for example, if you want to find out, let us say we have one element like this, 1 1 0, and another element is -1 1 2. So let us say this is my x and this is my y. So x transpose into y, can you find out very quickly? So that will be equal to 1 1 0 multiplied by -1 1 2. So if you do that, 1 into -1 is -1 plus 1 plus 0. So that is going to be equal to 0. So you can say x and y are orthogonal. Got it? So now I am going to give you a very important part of this particular special matrices that we have studied till now, and you have to keep this in your memory or in your notes. So you can write down here a special matrix and make this particular diagram to understand all of them at one place. Okay, so let us say this is my axis. Understood? And let us say this is my unity circle. Okay, so this is going to be 0 1 1 0, and this will be like what, 0 -1, this will be -1 0. So you understood like what is the index of each of the cut points, right? Now you know already that this is my real axis and this is my imaginary axis. Okay, or I can write it down fully. Got it? So I am going to talk about the eigenvalues of different matrices. Okay, so eigenvalues of different matrices will be what, that you will find out here. Okay, so let us say eigenvalues of all the skew Hermitian matrix is what, or first of all we'll talk about Hermitian matrix or symmetric matrix. So it will be real, right? So the eigenvalues will be real for symmetric or Hermitian. So if all the eigenvalues are on real axis, any number is fine, not a problem. I'm not talking about that. Then that will be for symmetric matrix. Got it? Now what about skew symmatrix? So all of them will be imaginary or 0. So I can say that this will be, this will be eigenvalues for skew symmetric. Skew symmetric. Or it can also be called for Hermitian, skew Hermitian. Understood? Then for nilpotent, what will be the eigenvalues? So for nilpotent, all the eigenvalues will be 0. Okay. And for idempotent, all the eigenvalues will be either 0 or 1. Okay. So this will be idempotent matrix. So either eigenvalues will be 1 or 0 for idempotent matrix. Okay. What about involutory matrix? So for involutory matrix, the eigenvalues will be either -1 or +1. Okay. So how shall I write it? Let us say I'm going to write like this. So you can see this one is going to be involutory, either +1 or -1. Then what is remaining? We had unitary matrix or orthogonal matrix, right? So for orthogonal matrix, I have told you that all the roots or all the eigenvalues will lie on the absolute one. So this will be the unitary matrix or orthogonal matrix or unitary. So the eigenvalues of orthogonal matrix or unitary matrix will be absolute 1, which will be on the peripherals of unitary circle. Okay, and you can see unit circle is what? Unit circle is nothing but my mod z is equal to 1. Mod z is equal to 1. Okay. So that's all. So this was all about eigenvalues of special matrices that we have studied, which is going to be including Skew Symmatrix, Symmetric Matrix, then Orthogonal Matrix, Unitary Matrix, Idempotent Matrix, Nilpotent Matrix, Involuntary Matrix, okay? And their eigenvalues are like plus minus 1, absolute 1, or real numbers or imaginary numbers. So anything that has been, like taught to you is all about this, okay? So this was all about special matrices. What we can do is we can take down the questions in our next session. Thank you.